All right, so welcome back to Engineering 270. Let's see. Good. All right, so let me start off with questions. Any questions from last time?
Not currently.
Okay.
I have a lot of questions about the language, but I think we're going to go over that today.
That's mostly what we're doing today, yeah. All right, did people get most of the way through or finished with Lab 1? Hopefully.
I got most of the way through and tried to do an experiment, but I need to know more about the language.
Okay. Yeah, and like I say, the new experiment for Lab 1 is probably the trickiest of the whole batch because we know so little about the language and MP Lab itself. But any kind of questions that you have about what the heck is going on with this, you can probably turn that question into an experiment. But we'll go through the language a lot starting right now, and that should certainly help. All right, so let's see. So at some level, the language is pretty simple, right? It's just opcodes and operands. That's really all we've got. We've also got a frozen camera because I'm moving my hand around and you can't see it. So let me restart my cameras. So really we have opcodes and operands, right? Opcodes are the action, the thing you want to do. Operands are the things that you do them to. So verb and noun. In fact, if you go back and you look at pictures of the old Apollo guidance computer from the Apollo missions back in the 60s, there's a button labeled noun and there's a button labeled verb. And those were, the opcode and operand input buttons, and that was the language that was used. Wow, my camera's really behaving badly. Give this a few more shots. So opcodes are pretty straightforward, right? Opcodes are basically the thing you want to do: increment, clear, do an exclusive or, that kind of stuff. Those aren't too hard to grasp. And the data sheet, will tell you exactly what each opcode does, and what it modifies in addition to its main function, and so on and so forth. The trickier part is usually the operands, the description of the thing that you want to operate on, and that can be pretty complex in some situations. So I'm just going to keep lecturing while my camera tries to figure itself out. So do you remember the distinction that we made in Tuesday? I mentioned in passing that there were sort of two main classes of computers based on the complexity of their instruction sets. Do you remember what that distinction was?
RISC and CISC.
Yeah, RISC and CISC. So RISC is a reduced instruction set computer, and CISC, C-I-S-C, is a complex instruction set computer. And the PIC processor is a RISC machine. It's a very simple instruction set. Now, an Intel processor, there might be, a dozen or more ways to specify an operand for an instruction. You might have an opcode like, clear, which says put a 0 into a register. But there might be, 10, 15, 20 different ways to specify what it is that you want cleared. On the PIC processor, there's really one way to specify an operand. There's really in most instructions there's one type of operand, and we can think of this as really just kind of one way to specify what that operand is. But sometimes we'll think of it as two ways, sometimes we might think of it as three ways, but it's really one type of operand, and that operand is called a file register. Yeah, I'm having some issues here. Give me a second. 1 second. All right. All right. I think this works. So if you look in the data sheet, or you look at the data sheet summary that that we've got posted in Canvas, there's a table 20-1 which gives you the format for instructions. So let me pull that up. And we looked at these templates a little bit the other day, but you know, and most of our instructions are what we call byte-oriented instructions. So there's an opcode and there's an operand, and the operand is mostly in these 8 bits, which are called file. They're represented with an F. And so if you look at, say, an increment F instruction, like this one right here, INCF, the coding for it looks like this, these 16 bits. So 001010DA, and then there's 8 Fs listed here on the data sheet. So let me write this out. And let's break this down. So let's say we want to say increment file register hex 23. All right, so the first thing to keep in mind is when you write an instruction like this, this is the opcode. It says increment something, add 1 to something. This is not the number that we're trying to increment. We're not saying add 1 to 23 and give me 24. This is an address of an operand. Okay, so most of these instructions, this is actually the address of the operand. So we have our memory over here. This is our data memory, which are also called file registers. Do you remember how many file registers we have?
256.
256. And they're just addressed from 0 all the way up to 255. So we're always going to work in hex in this course. Once in a while when we talk about timers, we might slip into talking about decimal, but we're pretty much going to do everything in this course in hexadecimal. So dust off your neurons on hex representation, right? 0 through 9 is just 0 through 9. 10 through 15 is A through F. So when I write 0x, that says this is a hex number. FF is, 15 plus 15 times 16, so this is 255. So 256 locations, we start with location 0, the highest is 255. So this is, what comes up again and again in C when you work with arrays. You're always off by 1 because you start from 0. All right, so we have 256 file registers, and this 0x23 is pointing to a location in this bank of data. And at location 23 hex, right, so 35 from the top, this is the thing that we're trying to increment. Whatever value is in there, add 1 to that value. So if this has the number, 7 in it, after you execute this instruction, the contents of this register changes to an 8. All right, that's all an increment does. If I execute this instruction again and the contents is an 8 to begin with, it'll change to a 9. And it'll keep incrementing until it gets up to decimal 255, and if I increment 255, it'll roll over to 0. because these file registers are only 8 bits wide. So if you have an 8-bit number like that and you add 1, you just come back to 0. Alright, so the important thing here is most of these instructions, when we say increment file register and we name an operand here, that's usually the address of the thing you want to increment. And so what we do when we code this instruction in binary is we take this address, and it's going to be something between 00 and FF hex, and we store those 8 bits of the file register's address into this part of the instruction. So yes, someone asked, would that be an overflow in this context? Yes, if you add 1 to this number and you get 0, you get a 0, but technically you've generated an overflow. And there's a way we can actually check to see if an overflow occurred. But it doesn't cause an error per se. It's just it just sets a flag basically. All right, other questions about this? I'm still messing with stuff. All right, so let's think about different instructions. So we know one opcode already. We've been picking on it since Tuesday. That's increment file register. And so you might see this written as just, INCF space followed by a letter F, which is a placeholder for, for example, 0x23 or 0x80 or 0 or 0xFF, right? But it's the address of the thing we want to increment. All right, well, a similar instruction is decrement file register. And so let me put some comments over here to describe what these instructions do. And in this case, it's basically saying take the contents of F and add 1. And let's put that back into F. And decrement is saying take the contents of F, subtract 1, and put that into F. All right, so those are pretty straightforward. Clear file register F says put a 0 into file register F. So if I say clear F 0x23, it doesn't matter what's currently in location 23. This is going to get written with all zeros. Okay, it clears a register. It resets it to 0. We're not ready to talk about DNA yet. We're coming up to that. But for now, we're not going to worry about those. So yeah, we'll need to specify what these bits are eventually. But for now, we're just conveniently ignoring them. I don't know, that's a good question. All right, so clear F sets a 0 into a file register. Set F loads all 1s into a file register. Usually, we initialize things to 0, but we might want to initialize something to be a bunch of 1s. So the setF instruction does that. There's a complement instruction, complement file register F, which means read the contents of that file register, complement each bit, change zeros to ones, ones to zeros, and then load that back into the contents of the file register. And then there's negate file register F, which says pretend that F contains a 2's complement decimal number. Take the negative of that number and load that into F. So what's the subtle difference between complementing and negating? This is a engineering 250 question.
2's complement, doesn't that add an extra 1?
Exactly, that's the only difference. 2's complement takes the regular complement, but then it adds one more. So negate is really like a complement followed by an increment. We don't need a negate instruction, therefore. We could, anytime that we wanted to take the negative of a number, we could just complement it and then increment it. It's sort of an extra instruction. Now, usually a RISC machine, has the bare minimum number of instructions that you need to write code effectively. So do we need a negative instruction? Well, if we're expecting that we might be doing a lot of work with decimal numbers and switching between positives and negatives, maybe it's worth, making your chip a little more complex to include this instruction. If we didn't anticipate that, if we thought this was going to be used with mostly logical values, we might not bother putting this instruction into our instruction set. Do we need a set F instruction, or is there some other way we could achieve this behavior of loading all 1s into a file register? How could we set without using a set F instruction?
We could add till the value is 256 or 255.
We could increment until we get up to 255. That would get us the same effect as this. Good. Is there another way we could do that?
Would bit set F also do?
We don't know about bit set F yet. But we could do a bunch of bit sets, yes.
0.
Say again?
Could you clear it, then complement it?
We could clear it and complement it. If we clear it, we'll get all 0s. If we complement each of those, we'll change to a 1. So there's, 3 or 4 different ways that we could achieve the same thing as this set F instruction. But the people who designed this chip felt that this is an operation that would be happening often enough that it was worth making a special instruction just to do that. So there's a moral to the story here, which is that in general there's many ways to do things in assembly language. And sometimes, there's one instruction, you can just use that instruction and you're done. But if there isn't, there's still usually more than one way to do something. And this becomes part of your signature, your fingerprint when you write code, is how you think about, breaking things down into smaller pieces. And there's nothing that's necessarily right or wrong in the approach that you take. Now some instructions can be done, some operations can be done, with a few instructions. Sometimes you can find a way to do them with a lot of instructions, and you'd probably want to do it with fewer instructions. But, it's a useful exercise to think about different ways that you can accomplish the same thing. So why do all instructions have an F at the end? Well, that's a good question. So these are really just kind of arbitrary names. They're understood by the assembler. And it turns out most of these instructions have an F at the end: MOVF, add F, clear F, and so on. But we're going to see some of these other instructions called literal instructions that end with a W, add LW, IOR, LW, and so on. And so mnemonics are interesting. Yeah, it's because F means file, basically. That's the direct answer. Increment file register. Yeah, go ahead.
So when it's using F, it's more so looking for pass by reference, kind of. The other letters are values, right?
Sort of, yeah. So, I mean, INC is kind of like the actual, description of what the opcode is going to do, and the F is saying we're doing it to a file register. But it's really just kind of meant to be kind of a human readable abbreviation for, increment file register number such and such. Assembly language, the whole goal of it is to have a language that's very close to the level of what the machine can understand. But we don't want to force programmers to write ones and zeros, so we give them, something kind of human readable, human writable, and we give them a tool called an assembler, that's part of MPLab, that will translate from here to the ones and zeros that the machine wants. All right, so this is one set of instructions, right? And they're pretty straightforward to understand what they do, right? Add or subtract one, clear something, load a value, that kind of thing. There's a few other instructions like this I want to talk about: swap and rotate, and these are a little bit peculiar. So, tell you what, let's go ahead and do an attendance check. So go ahead and send me a direct message, private message, with your canvas name, dash, and the word here, H-E-R-E. Okay, and let me know that you're here, and I will get my scissors and do a prep.
Do we do it in the general chat, or
No, do it as a direct message.
how do you do that again?
Let me see. So down at the bottom of my chat window, it says 2 colon.
I see it.
Yeah. All right, cool. Thank you. And if you weren't here on Tuesday, if you're going away from keyboard, just do the same thing. Send me a direct message with your canvas name, dash, and just prefix it or suffix it with AFK to say you're away from your keyboard. And then when you come back, just send me another note and say you're back. And this way, if you happen to be out of the room when I do an attendance, you don't get dinged for it. All right, cool. Thank you. All right, so let's look at swapf. And opcodes, it doesn't matter in MPLab if you make them uppercase or lowercase. So I can say INCF, I could also say INCF. And it's just kind of personal taste. So what does swapf do? Suppose the contents, and we're still looking at the contents of a file register. Suppose my file register contains the following bit pattern. All right, so there's 8 bits in my file register. Here's what swapf does. It breaks it down the middle, cuts it in half, and it takes what was on the left and puts it on the right. So it changes this 8-bit number into this 8-bit number. And if I were to do swapf again on this number, it would change it back to this original number. So it's a way to take the 2 half bytes, which are technically called nibbles, take the 2 nibbles and swap them with one another. Okay, that's what the swapf instruction does. And that actually turns out to be a really useful thing to do. We'll see why next
I was
week.
about to ask, like, what context is this used in?
Well, so I won't wait till Tuesday. I'll tell you now. This is used mainly when we're representing numbers in binary coded decimal. And remember, in BCD, if I wanted to represent the number, say 57 decimal, I would represent it as 2 digits. I'd write the first digit in binary, that's a 5, and then I'd write the second digit a 7, like that. So this is the number 5. and this is the number 7. Now, it's not standard weighted positional notation, right? It's not, 1, 2, 4, 8, 16, 32, 64, 128. It's a different way to represent decimal numbers. But it's a convenient way sometimes because now, if I want to know what the second digit is, it's just these 4 bits over here. Well, when I'm taking this apart, sometimes, I'd have my first digit here, my second digit here. If I want to work with this digit, it's easier to do sometimes if it's sitting over here in these 4 positions. Because now I can do something we're going to talk about later called a bit mask to basically throw away this upper part, make this all zeros. And now I've got what originally was this most significant digit sitting down here, like just a plain old 8-bit number. So we'll see some more specific examples of that later. All right, so that's swap file register. Another useful instruction. Rotate left with no carry file register. So what do we mean by rotate left with no carry? Well, let's take another number. Let's suppose my number is suppose there's my 8-bit number. If this is the contents of a file register and I say rotate left with no carry file register, here's what it does. It takes this bit from the end. Sorry. I did a rotate right. Alright, suppose this is your number. Rotate left basically takes this bit, puts it over here, shoves everything over left one spot. So it changes that original number into this number.
So it's kind of like a bit shift.
It's exactly like a bit shift. So it changes this into that. And the effect is basically taking everything and just moving it over one spot, but then this thing on the left that would have fallen off gets wrapped around back here to the right. And there's a rotate right, no carry file register, and you can imagine what that does. Right, it takes your number and it shoves everything over to the right. So if this is your original number, it bumps all of those bits down and takes that bit that would have fallen off and brings it back over to the left. And those are useful for taking apart a number one bit at a time. We're going to talk more about bits versus bytes on Tuesday, but it's usually easy to work with something if it's sitting on the right side of a byte. Right? It's pretty easy to work with something if it has, a value down here or in these two rightmost bits. So we use these rotate instructions sometimes to take things that we're interested in. Let's say we're interested in these 3 bits here, and we could rotate those down until they're in the rightmost 3 positions. And then we have our number looking like that.
What does it mean by no carry?
There is a place inside the CPU. It's like a single flip-flop, and it's called the carry flag. So no carry ignores the carry flag. It does exactly what we just saw. If I say rotate left with carry through F, and let's suppose that my number is this, and let's suppose my carry flag, it's a flip-flop, it's a 1 or a 0. Let's suppose it's a 0. And so here's the contents of the file register. Here's the carry flag. If I say rotate left through carry, same thing happens to F. Everything gets shoved down one spot to the left. But this bit that would fall off the end, instead of coming back here, this bit goes into the carry. And the value that was in the carry comes over here onto the left. So it's like a 9-bit carry. Or a 9-bit rotate. So you shove everything to the left, but the leftmost bit that falls off, instead of going back to the beginning of the number, it goes into the carry flag. And the previous value of the carry flag, that's what fills in the space at the right side of the number.
I assume we would probably use something like this when we have an overflow.
You can use this to handle overflow, definitely. And so it pops up, you know, when we're doing addition of numbers by hand. This is how we can tell that something overflowed, or something will overflow, right? We can take this leftmost bit and we can throw it into this carry flag, and this carry flag is special because we can use this to do conditional instructions. To say, if this is a 0, then do this thing. Or if this is a 1, do this other thing. And so that'll help us in particular if we wanted to add numbers that were bigger than 8 bits. Let's say we had two 16-bit numbers. And we wanted to add them together. Well, you know, we're going to add these 8, we're going to add these 8. But if there's a carry coming out of here, we've got to do something special. So yeah, it'll work with all kinds of arithmetic operations. Let's see, can we rotate all 3 together, or would they get reversed because we do it one by one? Rotate all 3 what's together? So you're rotating one file register, and then optionally involving this extra bit here. And so the effect of the carry flag is, you know, do your rotate, but think of this as a 9-bit number. So this wraps around over to here, this goes in here, everything else moves down. So excellent, yeah. So if we're interested in 3 bits, let's say for some reason we've got a byte, and we're really interested in the values of these 3 bits. And we don't really care what's in these bits or those bits. So we could rotate this to the right 3 times, which would change this to, you know, the 3 bits we care about and then our other bits. Or we could rotate it to the left 5 times, and that would work. But I don't think they get reversed. This should work. This should work just fine. So if you like,
would it be more efficient to do this in like a loop, like you did in our first assignment, than to just write out 3 statements, because that would be more costly on the program memory?
Well, it depends. It's sometimes 6 of one, half dozen of another. If you want to rotate something twice, just write 2 rotate instructions. If you wanted to rotate something, you know, 100 times, you definitely want to write a loop. But for rotates, there's no reason to do that, right? Because once you rotate it 8 times, you're back to where you started. But for some other instructions, yeah, there's definitely going to be cases where it's more efficient to write a loop. It'll take less space in program memory. And it really kind of depends on the particulars of what you're trying to do. So yeah, if we do a rotate, then things move down, but everything is still in the same relative order. So that works well to preserve. Okay, this is good. These are excellent questions. Keep them coming.
So, like rotate with a carry is just a traditional bit shift, right?
Not exactly. So a traditional bit shift to the left would always load a 0 in to the vacated position. But if we wanted to achieve a traditional bit shift, we could clear the carry flag and then do a rotate with carry, and that would load a 0 in. So some processors differentiate between shift and rotate. And we're always doing rotates. We're always somehow using the bit that's getting tossed off the edge, and we're bringing it back into something, either back over here or loading it into the carry flag. A pure shift, and we don't have pure shifts on the PIC processor, a pure shift would say shift everything over, it would always load a 0 into here. So slightly different operations, but we can do rotates with shifts, we can do shifts with rotates. And again, a CISC machine would have both. A reduced instruction set just gives you one, and you have to do extra stuff if you want a different operation. So if you're starting to, yes, you can set the carry, and we will do that often. But we're gonna have to talk about the status register, because the carry flag is just one of several flags that we'll be interested in. But yeah, there's a way to set it, there's a way to clear it, and there's a way to check its value. So you're probably starting to get the idea that this is not a high-level language, right? Assembly language is about taking, a small collection of tools, which we call instructions, and figuring out how to put them together to do something, right? And this is the essence of programming. This is the essence of physics. This is the essence of engineering, is breaking problems down into smaller pieces until the pieces are small enough that you know how to solve them, and then putting those sub-solutions together to make bigger solutions and working it back up to, the solution to the original problem. And that's all we're doing in assembly language in this class. We're just going to keep breaking things down to smaller and smaller pieces until we can describe what we want to do in, terms of instructions like increment or clear or set or rotate or things like that. Oh, good question. Yeah. No, there's a single carry flag, so it's not part of the file register. It's a separate flag. It's just a flip-flop inside the CPU, and it's shared by everything basically. All right, so, most of these instructions, the operand is a file register, but we sort of think sometimes of having a second type of operand. And so here's the motivation for this. We have 256 file registers, right? And when we look at the coding of an instruction, we see there's 8 bits allocated to specify the file register. So, if we're incrementing 23, we'd put hex 23 into these 8 bits, and then here's the opcode, and here's the mysterious DNA bits. Now suppose, we want to do something that works on 2 pieces of data. Suppose we want to do something analogous to in C, x equals x plus y. So we want to read the current value of one register, read the value of a second register, add them together, and store the results into X. Is there any way that we can design an instruction on this processor that would do something like take X, add Y, and store the result back in X. Or let me put that different.
Do you mean like two operands in the same statement?
Two operands in the same statement. Is that possible?
Possible, because you only have 8 bits to access memory addresses, and memory addresses are 8 bits.
Yeah, so we're going to need 8 bits to specify the location of this operand X, and we're going to need another 8 bits to specify the location of this file register Y. So just to specify the two operands is going to take 16 bits. Well, how many bits do we have in a typical instruction?
Only 16?
Only 16. So how many bits do we have for the opcode? None. So we've got a problem. Most of our instructions won't allow us to specify more than one operand. And so how the heck are we going to do something as simple as saying, let's take X and Y and add them together if we can't specify two operands?
Would you, like, stick X in a certain register, and then add Y to that register, and then assign that register back to X?
Okay. So put X into a register, add Y to that register, and then put the register back into X. So what is this register that we're going to use?
Is it WREG?
So that's what the W register is. So we have a special operand, and it's really not, but we're going to think of it as a special operand called the W register. This is the working register. In older machines, it was sometimes called the accumulator. And we can specify that we want to use the W register without using 8 bits to specify it as an operand. In fact, there's a way to use a single bit to specify that one of these operands should be the W register. Okay, and that's what this mysterious D bit is when we look at the coding of instructions. So if you go back here to the description of byte-oriented operations, which is, increment, that kind of stuff, this bit D, if it's a 0 or a 1, that changes where the destination is. Okay, so what's a destination? So you got to think a lot about read, modify, write. So we have an instruction like increment file register. So let's just say we're incrementing a file register. I'm just going to use Z as the name of a variable. And this means take Z, add 1, put it back into Z. Well, we usually think of this as, wave your magic wand and now 1 gets added to the value of Z. But what's really happening here is 3 things. We read the value of Z. So we get the value that's stored in this file register. We modify it by adding 1 to it. And then we write it back into that file register. It's a 3-step operation. All right, so read, modify, write. That's what most of our instructions actually do. This is like super critical when you think about computer architecture and when you start trying to design, a state machine that's going to become a computer. This is also super critical when we get into event-driven programming and working with objects in Java and thinking about threaded operations and trying to make sure that multiple threads run safely. We'll come back, a year from now if you're in 223. And we'll talk about read, modify, write in that context. So this is a pretty key idea. For us in assembly language, what it means is that there's 3 steps taking place. Go into the collection of file registers, wherever this address is for this variable Z, pull that out. Okay, load that into the system. And then run it through some circuitry to add 1 to it. Right? You've built adders in 250, so run it through that kind of circuit. and then take the output of that circuit and put it back into that location in memory. All right, this D bit in our coding lets us change what this instruction does. It lets us say, should we write the result back into Z, or should we write the result into this special register called the W register, or the working register. And we can specify the behavior with a single bit, and that bit is this D bit. So if D is 1, then this instruction, whatever the instruction is, does exactly what we've been doing. It takes the contents of a file register, it modifies it in some way, increment, decrement, clear, swap, etc., and it writes the new value back into the file register. But if we set this D bit to a 0, the file register itself is left unchanged. And instead, the modified value is written back into the W register. All right, does that make some sense?
Where exactly does the D and A bits go? Like, right next to the operand or right next to the operation?
It depends on the instruction. But, you know, back in our first increment instruction, when we were coding increment 001010, those 6 bits specify increment, and then the D bit is the 7th bit in this 16-bit pattern, and the A bit, which we're still not going to talk about today, would be the 8th bit, and then these 8 bits specify the address of the file register that we're incrementing in this case. But it depends on the instruction. So these byte-oriented instructions, the D bit is always here, the A bit is always here, the opcode is always 6 bits. But there's some other instructions where this will change. And if you come down into table 20-1 itself, right, for each instruction you can see the exact coding, and it shows you, you know, a D and an A, for example. Now, some of these instructions don't have a D bit. Right, 0110-101 has an A bit. There's no D bit for the clear instruction. So we can't clear a file register and say store the result in the W register. Well, it would be kind of a silly thing to do, because we could just say clear the file register, clear the W register directly. So these patterns over here show you exactly what the 16 bits are for each instruction. But yeah, generally the D is sitting here right next to the opcode. Alright, so we can specify a different destination. We don't have to just take a register, modify it, and store the modified result back in the register. We can choose where that modified value should be placed. And so we can say something like increment file register 23, comma W. And that would say add 1 to the contents of this file register, but don't change the file register. Instead, take the modified contents, put it back in the W register. And WREG is just this magic 8-bit register sitting down here inside the data path of the CPU. So it's sitting right here. And it can go into the arithmetic and logic unit to be combined with other things that might come from, you know, the file registers. All right, so let's take a 5-minute break, and then let's start digging into how we can put some of these instructions together, looking at opcodes, file registers, and the W register, and see how we can start doing some of these higher level behaviors that we might want to do. And then let's talk about this next type of instruction, which is called a literal instruction. But those are easy after we're done with these kinds of instructions. So let's take a 5-minute break, and we'll come back at 12:55. And you don't have to tell me you're AFK during a break if you're going to be back. All right, welcome back. All right, so let's look at using the W register. And usually when you look at code in the book or you look at code in the lab, instead of saying comma W, you usually see comma 0. Now, uppercase W should be set up as a default for 0, but most commonly you just see it written as a comma 0. And if you don't specify a comma 0, the assumption is that you just want to increment the file register itself. In other words, the destination bit is a 1, so the result's going back into the W register. So this comma value that you put over here, the thing after the comma, is really the value of the destination bit. The assembler will default it to a 1, so if you want to write the results back into the file register, you don't have to put a suffix at all.
So that's the D bit, right?
That's the D bit, right. So the default for the D bit is a 1. If you want to force it to a 0, you got to say comma 0 after your operand. All right, so let's look at some examples. Let's add file registers 23 and 24 and save the result back in file register 23. And there's an add instruction, by the way. I should show you all of these first, actually. So there's a new batch of instructions, and these are the instructions that don't really make sense unless we have two operands, but they still have the same basic structure. So, for example, add WF, add the W register to a file register. Subtract WF, subtract the W register from a file register, and so on and so forth. So let's just play with addition. So we have an add WF. So how could we add the contents of these two file registers together and store the result back in file register 23? Toss out some ideas.
We would need to take file register hex 23 stored in the working register, then we add file hex 24, and then we move hex 23 back, or what's in working register back to hex 23.
Cool. All right, so the suggestion was copy the contents of file register 23 into the working register, and then use our add WF to say add the working register to the contents of file register 24. Store the result in the W register, and then copy that result from the W register back into 23. All right, so we need one more instruction to be able to do any of this, and that's move WF, move the W register to file. That will let us copy a W register into a file. But move F, just MOVF, the description of that is move the file register. Well, if we move the file register, if we say move F file register comma 0, that will copy the file register into the W register. So let me put a little sidebar here. If we say move WF and we just specify a file register, this says copy W register to file register F. If I want to go the other direction from a file register into the W register, I can say move F, F comma 0. This says copy the file register F to the W register.
So remind me again why you move it to W register and then move it back after the
So the suggestion here was to add 23 and 24 together and store the result in 23. First we're going to put 23 in the W register, and then add 24 to the W register, and then store the result back into 23. The reason we're doing that is because the only add instructions we have are ones that work with the W register. There's no add instruction that says add this file register and that file register together.
Okay.
You say
So-
that the W register is kind of like a holding cell for things that you just
Exactly.
want to add to things.
Exactly, yeah. So it's called the working register. That's what the W stands for. And it's a temporary register that we can use however we like. But it's usually used, you know, to hold something so that we can operate with that held value and some other typically file register value. Let's see, do we need to clear the W register? It depends. If you need a 0 in there, then you've got to put a 0 in there because there's no way to predict the contents of any file register when the machine starts. So if we needed a 0 in there, we would have to put a 0 in here. But to do something like this, to save this into the W register, using a MOVF instruction, there's no need to clear W first, because this will replace the contents of the W register with the contents of the file register.
No, I'm a little confused about the move F to F being copy reg to file reg F. Is it because of that W that's making it the register?
Yeah, this is a different opcode, MOVWF. And this instruction only does one thing. It reads the W register and copies it into a file register. So it's a separate instruction from this one.
Okay. The F was just making me look confused.
Yeah, I probably should have called it something other than F. All right, so let's look at examples here, right? And this is really confusing to most people until you've done it, you know, a half dozen times or so. These kind of sound like the same thing. So let's write some code to correspond to these. So copy file register 23 to the W register. So I'm going to say MOVF hex 23, comma 0. Okay, so I'm saying the destination bit is a 0, so the result of this move is to copy the contents of this register into the W register. And then I'm going to say add the W register to a file register. I'm going to specify the file register I want to add to. And I don't want to change the contents of register 24, so I'm going to put the sum back into the W register. So now the W register is the sum of these two things. And now I'm going to say move the W register into file register 23.
Is that add WF?
Mm-hmm.
Okay, sorry.
Yeah, no, it's okay. And those are the only adds that we have. We have an add WF with carry, but we don't have an add, you know, two file registers together.
Why? Oh wait, I understand. Never mind.
Okay, cool. And let's see, question in chat, can we define variables? Yes, and we will get to that today, so that we don't have to have magic numbers scattered around. We can say, you know, X means hex 23 and Y means hex 24. And then we could say move X comma 0, add Y comma 0, and so on. All right, and another excellent question in chat. Would it be quicker to move 24 into the W register and then add it to 23? Sure, absolutely. So we could do this. We could move file register 24 into the W register. And then we could say add W register to file register 23 and not put the comma 0 at the end. And so what does this do? It takes the contents of this, puts it into W, and then this adds that to file register 23 and puts the results back in file register 23. So hey, we did the same thing now, but with only two instructions.
Is
So
there a
that's-
way to account for overflow if it happens during like adding here?
We can check a flag, like the carry flag, to see if an overflow occurred. And then if you cared about it, we could put some statements over here saying if an overflow occurred, then, you know, go over to this section of code and do something. It's actually going to turn out in most cases we're not going to end up worrying about overflow. But if it's a concern, yeah, we can definitely check for it. So here's a way to do this with 3 instructions. Here's a way to do it with 2 instructions. Not a real big deal in the end, unless, you know, you're doing 1,000 things like this, in which case it might be a huge deal. So this is going to be less memory, and we've only got 4,000 bytes, so enough space for 2,000 instructions. So this takes less memory. It's also going to be faster. It's going to be 2 instructions instead of 3. And you can start to imagine all kinds of different ways that we could perform the same operation of adding 2 file registers together, right? We could clear the W register, and then we could add the W register to 23 and store it in the W, and then we could add the W register to 24, and then we could put the W register back into 23. Alright, so how about if we wanted to add the contents of file register 23 and 24 and save the result in file register 25.
You would move either 0x23 or 0x24 to the working register, then you would add the other, and then you would do a MOVWF to the given destination x25.
Cool. Alright, move say 23 into the W register, add the other file register to the W register, and save the result in the W register. So now W has the sum of these two, and then move the W register into 25.
Couldn't you also move OX23 into a W register, add it to OX24, and then just move OX24 to OX25? Or would that just be too many bits?
You could, but that would be changing the value of 24. If you didn't use the W register here.
Okay.
So this is a good point to bring up. So that would be called a side effect, right? At the end, so let's do this. So hypothetical, right? Copy 23 in the W register, add the W register to 24 and save the result in 24, and then copy 24 to 25. So the end result would be that we've accomplished this. But there's another effect, there's a side effect, which is the contents of file register 24 has been changed. And so even if you're not told explicitly, the general rule is you should try to avoid side effects. Right? If you're asked to write some assembly language code to do this operation, you should assume you're not allowed to change these registers. And we don't always say this explicitly when we write homework questions and such, but generally you don't want to disturb anything unless it's an intentional effect of the code you're writing. So keep that in mind, because like I say, it's not always explicit. All right, so commenting. So let's say you're writing assembly language code, and your goal is to add the contents of 23 and 24 together and store it in 25, right? You're going to translate that into these 3 instructions. if you come into this code from outside, if you hand this code to somebody and they start working with it, and they know how to program pick processor, right? They understand that this is going to take the contents of this register, put it into W. This is going to take W and add that and put it back, and so on, right? They can understand what each instruction does. What they're not going to understand just by looking at this, though, is why you're doing these statements. So what you would typically do is you would add other things into your program, comments, which have no impact on the CPU itself. They're completely ignored once your program is turned into ones and zeros, but they're meant for a human who's reading this to better understand what your code is doing. So you might put a comment in the beginning. Remember, comments start with a semicolon, which says, you know, add 23 and 24. Save in file register 25. But, you know, a better comment would be, because the person reading this doesn't know what this is and what that is and what that is. So a better comment might be, you know, add X and Y. Save in Z. Or add the two scores that we've calculated and save the result in a running sum. Or something, you know, that describes to the person what it is that's going on here. What are these 3 lines of code intended to accomplish? And then, you know, down here, I might say something like, you know, first score, rounding factor from curve, and then this is the adjusted score. And maybe this is, you know, part of an assembly language program that's used for grading a class, right? And so when I'm going through this as a programmer or a maintainer or someone who's developing more code on top of this, right, I'm looking at the comments over here. I'm saying, okay, we're getting the first score from the student, and now we're you know, adding in some adjustment from a grading curve, and now we've got the adjusted score, right? So, you know, when you write C code, you want a lot of comments in your program. Basically, any time that there's something that's not obvious. When you write assembly language, you probably want to comment on more or less every single line of code. And you don't want a comment that simply repeats, you know, what the instruction is doing from the manual. You want a comment that explains why you're executing this statement. Yeah, go ahead.
Commenting is just this weird symbol. I forget what it's called.
Semicolon.
Yeah.
Yeah, so it's just put a semicolon, and then you can put anything you want after that.
Cool.
And it's this whole idea that, you know, we're taking some complex problem and we're breaking it down into smaller and smaller pieces until we get to these very, very, very tiny little blocks. And why do we have these 3 blocks right here? Well, that's what the comment will tell you, right? And coming back and trying to read this stuff later on, right? I mean, this all looks the same, right? Picture, you know, 10,000, 100,000 lines of code that just look like this and go on and on and on and on, right? It's mind-numbing. So good commenting, right, will help you work with this code. It'll help you while you're writing it. It'll help me while I'm grading it, and so on. And it's almost impossible to have too many comments in assembly language. And it's extremely common to have more lines of comments than you have actual lines of code. That's not a goal, it's just kind of a reality. Alright, so let's keep playing with this. So let's take the contents of 4 file registers and add them together into a big running sum that we're going to store in file location 80. Can you do multi-line comments? I don't know if this assembler understands like a slash star, but it's not unusual to, you know, make a comment block by just putting a semicolon in the front of each line. It looks pretty typically assembly-ish. All right, so a running sum is a common thing to do in programming, right? You want to accumulate a bunch of numbers together or something like that. So here we might want to do something like clear file register 80. Put that into the W register. So that's our running sum. And now we're just going to start writing a bunch of add instructions to add all these things to our running sum. So we can say add WF23 and put the result back into W. Add WF24. Hey, you know, if you're good with VI, this takes nothing to, you know, copy and paste and just change the address here, just change this bit and so on and so forth. So I can, you know, have a bunch of things that I'm adding together. And, you know, here I might say WREG equals final sum. And then let's store that into file register 80. So we'll just move WF into hex 80. Oh, poor cat. All right. But you know, again, there's other ways to do this. We can slice this a lot of different ways. And when you have a compiler, like if I wrote something in C that tried to add a bunch of things together and store it in 80, depending on the nature of the compiler, you might get code like this. You might get code that takes a lot more instructions. You might get code that says, you know, copy register 80 to W, add 23 to that, put the result back in 80. And then copy 80 to W, add 24 to W, put the result back in 80. And then copy 80 to W, add 25, put the result back in 80, right? And you would get the same result in the end, but you'd end up taking a lot more instructions and a lot more time. And humans will generally do, well, it's possible for a human to do a better job writing assembly language than a compiler, right? It depends on the specifics. But, you know, writing something like this in C is definitely a whole lot easier than figuring out how to write something like this. But eventually someone or something somewhere has to make a translation from this to this. So we're just, you know, getting good at doing this translation ourselves.
I have a curiosity question.
Sure thing.
Even though we're not talking about CISC, do some complex instruction sets specify more operands?
Definitely.
So like slim this down?
Yeah, absolutely. So a lot of instructions, and the processor I grew up on was called the VAX. By Digital Equipment Corporation. It was the VAX 780. And, you know, any instruction, any opcode could take 3 operands, 2 sources and a destination. And you could specify them not just as addresses, but you could say, take the contents of this register, use that as an address in memory, go to that location, add the contents of this, use that as an address, and that's my first operand. And then I could do something similar for the second and something similar for the destination. That was called an orthogonal architecture. You had a bunch of ways to specify operands. You could put any of those together with any instructions. Super complex instruction set. But, you know, the most popular processor of its time. All right, so let's talk about technical term, labels and symbols and stuff. And somebody asked earlier if we can have variables, and yes, we can. And you'll see these a number of different ways in code in the lab and so on and so forth. So yeah, we can do variables, and when we write assembly language, so mostly we're writing opcodes and then operands. So do an exclusive OR with some file register and put the result back into the W register. But there's some things that we put in our assembly language program that don't actually generate code. Okay, this MOVLW, this MOVF, this exclusive OR, and so on. Each of these is going to generate, a 16-bit pattern of ones and zeros that corresponds to that instruction. ClearF port A is going to generate a 16-bit number that's going to get loaded into the program memory. Okay, so most of these instructions generate machine code. Comments don't. Okay, comments are pretty much completely ignored. But there's a few other statements we can write in this program that don't actually generate ones and zeros, that don't actually create instructions to go into the memory. Okay, one of them is org, O-R-G. And org is the origin statement. It basically says, where in program memory should the instructions you're about to see get saved? And so if we say origin 0, then when we write this instruction, clear file register, and it gets translated to 16 ones and zeros, it's going to get stored where? Location 0. So for the beginning of the course, most of our programs are going to have an origin 0 statement somewhere near the beginning. And that's going to say, hey, anytime that I write an instruction after this, put it at location 0. And then the next instruction will go at the next location after that in memory. And these will just get stored one after another, unless somewhere down here we have another origin statement. If here I say origin 500, then this statement will get stored at location 500. Okay,
Is there a reason to do that?
Yeah, there will be when we start talking about interrupts. So there's a few special locations inside the PIC. Location 0 is where your program starts when you power it up. So that's where we want most of our code to begin. So when you first apply power, it reads that first instruction. But there's other types of code we're going to write which are called interrupt handlers, and those need to go at very particular locations. So locations 8 and 18 have special meaning. The other thing is, if you're working on code with somebody else, one person might be developing one set of code, you might be developing another set, and you might have to arrange where that code is going to be stored in the program memory. Because you can't write both of your sets of code and have them start at 0. So you might say, okay, I'm going to start at location 80, and you're going to start at location 60, and so is going to start at location 0. So origin is another one of these. Sorry,
so
go ahead.
The origin statement have to deal with program memory, not data memory?
It only has to do with program memory, correct. And really important distinction there, right? Program memory, data memory, totally different beasts. So origin says, where do we store these instructions in program memory? And once it's decided where to store one instruction, consecutive instructions just get stored at consecutive locations.
I see that a lot of the defines have 12-bit addresses, I guess.
Yeah.
Like, hex bits.
Right, and we're not ready to talk about that yet. That's going to have to wait till Tuesday, but it has to do with that last mysterious bit called the A bit, or the access bit. Because I kind of lied to you a little when I said there's 256 file registers. There's actually a few more. And so we actually need 12 bits to specify a file register location. But that gets into a really, really nasty rabbit hole. So we'll come back to that. We'll come back to that Tuesday.
That's like a preprocessor stuff with the defines, right?
So the define is a preprocessor. Define is just like define statements in C. It's saying anytime you see uppercase PORTA, replace it with 0xF80. It's really just a symbolic replacement.
I have another question.
Okay.
If you have another section of the program like ORG hex 500 somewhere down the line. Do you still have access to those defines up above?
Yeah.
In that section.
Yeah, it's all just one big file. So everything is basically global.
Interesting.
And then somebody asked, would you have to memorize where your code ends to make another file that works with this one? Yeah, basically. And this is part of what happens with the linker and the loader, is if you have multiple C programs and you put them together, something needs to keep track of, you know, this program goes from here to here, and this other program goes from here to here, and how do we tie those together, and so on. So in assembly language, we've got to do all of that ourselves. So again, it's just really kind of like low level. All right, so down here when I say MOVWF count, well, count has been defined to mean hex 80. So this statement is exactly the same thing as saying MOVWF 0x80. But the word count's a little easier to deal with than 0x80, right? Especially if we know that this means the count of something, right? Then when I want to, you know, copy the count in the W register, I just say MOVF count, comma 0. They don't have to be uppercase, but they have to be consistent. If I call this, you know, lowercase count or count with an uppercase T, I have to use the same casing down here. But I could have, you know, 3 different counts with different uppercase, lowercase, and they'd be 3 different variables. This is part of the style, right? So when Izad writes this code, he likes to uppercase everything. So opcodes and operands tend to be uppercase. Some of these, which we'll talk about on Tuesday, like tris B and tris A, have to be uppercase because they've been set up elsewhere for us. I don't know how long names can be, but I don't think there's a reasonable limit. I think if you went out, you know, 20 or 30 characters, it would still be okay.
Because they're just getting replaced, right?
They're just getting replaced, yeah. And 2021 software tools are usually set up to deal with, you know, most reasonable limits. Now, in older days, you know, this might be limited to 8 characters or something like that, but I don't think there's limits imposed. All right, so number sign define, these are symbolic replacements. They're just like the define statement in C. These things that start, and these have to start in column 1. Okay. Radix is another, what we call an assembler directive, right? So these are assembler directives. They are not things that turn into machine code. They're things that tell the assembler, MPLab, what to do, or modify what MPLab's going to do. And so radix is a statement which says, hey, if you see a number without a decimal point on it or without a 0x, assume it's hexadecimal. I could say radix dec, and then if I typed a number like 10, it would take that to be the number 10 decimal. If I say radix hex and I do the number 10, it's going to take it to be 16 decimal, 10 hex. And there's, you know, a whole book you can download filled with all the different assembler directives that are available. And there's a whole macro package for this assembly language where you can not just define symbols, but you can make little functions that will generate code for you and all kinds of stuff like that. We don't go into that in this course, but there's a lot more to this language than what we're covering. But this will be enough to get you through. The other thing which you'll see is the statement EQU. And we can say something like, you know, count EQU 0x80. And it's almost the same as a number sign define. You can probably think of it as being interchangeable, but you'll just see this used sometimes instead of a pound define. And this basically says, you know, in the code from this point on, if you see the word count, I mean location hex 80. So you'll see that used more or less interchangeably with pound define. So now we might do something like this.
Wait a minute.
Yeah.
So like, EQU is the name that it's defined as, right?
No, so count is the name. It's equivalent to hex 80.
So it's defined count as hex.
Mm-hmm.
Okay.
Yeah, so this is kind of the same thing as define count hex 80. The real difference is this is much more general purpose. This doesn't have to be a file register location. I could put, anything in here. I could put code in here if I wanted. I could make up my own opcodes. I could make an opcode called NIC that increments a file register. I could say define NIC as INCF. And every time I want to increment a register, I could just say, NIC hex 23. So counts are much more specific. They're really defining a location of a file register.
So is define like an assignment statement?
Define is what we would call a preprocessor statement. So really, before anything gets done, something runs through all this code, and anytime it finds port A, it replaces it with this. And anytime it finds port B, it replaces it with that. And so this becomes 0xF80, this becomes 0xF81. And then after all of those things have been replaced, then it goes ahead and it tries to assemble all of this code.
Okay, thank you.
Yeah.
So it's just basically renaming these things.
It's renaming those symbols, yeah.
Okay.
And so yeah, this is being handled by the IDE. This is being handled by MPLABX long before it ever actually gets to the chip.
Can you have like a running total? So like if you have 3 variables and you just want to define a sum of all 3 of them, you can do that too, right?
Define in what way?
So like you have 3 variables, define sum as variable 1 plus variable 2 plus variable 3.
So if I do that,
I think you can do that in C.
so I can do this, and then if I say something like, move file register sum into 0, what that's going to do is the preprocessor is going to go through, it's going to change the statement into the following.
Your page is in the way, by the way.
Oh, thank you. So I could say define sum as x plus y plus z. And then if I say MOVF sum comma 0, this statement is going to get rewritten by MPLAB into the following. MOVF x plus y plus z comma 0. And that's going to give me a syntax error when it tries to assemble it, because that's not valid assembly language. So these things are just blind replacements. Anytime I see the word sum, replace it with that. But this is not valid syntax, right? There's no such operand as x plus y plus z, and doing this doesn't get you around that limitation.
That's why it works in C and not in this.
Yeah,
language.
yeah.
Interesting.
Yeah, exactly. But we can use these defines or EQUs to make our life easier. So, well, I'll stick with define since that's what we've got in Lab 1. So let's define x to be 0x23. Let's define y to be 0x24. And now I want to set x equal to x plus y. So now I could do something like move file register y into the W register, and then add the W register to x. And this is, a little more agreeable to read than, something with 23, 24 stuck inside there. So we'll use these preprocessor, these assembler directives throughout our code, and they just make things a little more readable. these things down here, these are labels. We'll talk about these when we get to controls, but, you know, we've mentioned that instructions are executed one after another most of the time, but there's an exception. For example, if we have the go-to statement, it says, hey, let's not do the next instruction. Let's go back to somewhere else and execute instructions from there. Well, where should it go? It should go to whatever location this instruction was stored at. Well, how do we know that? Because we put a label here called loop, and when we say go to loop, well, the assembler knows, okay, so here's a label loop, here's the next instruction. Where did I put that in program memory? That's what it's going to use to code the go-to statement. So we'll talk about go-to instructions and control statements in general next week. We don't have to worry about them yet. And you don't need them for your homework. Yeah,
I
good.
was going to ask you the difference between go-to and call, but I guess we'll get to that next week.
We'll get to it next week, but calls are like function calls in C. So they are a go-to, but they remember where you were before you did that go-to. So that when you say return, you can go back to where you left off. Go-tos are just a straight branch. They just jump to another location, and there's no record of where you were. But we'll spend at least one whole class just talking about calls and returns, because they get into all kinds of other things. And yeah, good question, good answer in chat. So do you plug the chip into your computer? It depends. But for this particular chip, there's a thing called a programmer. It's about this big. It has 6 plugs on the side that you put wires into, and you connect up to 6 pins on the chip on a breadboard. And then you take the other end of the programmer, you hook that up to your computer through a USB cable. And then in MP Lab, there's a little icon with an arrow on it. If you click that, it'll take the 1s and 0s for your program, send it through the USB port to the programmer, and then the programmer will condition that information, use those 6 wires connected to the chip to actually program it and load the memory. It's a really cool process.
Program memory, like flash memory, so you can just flash your program to
Yep.
it and it permanently runs that?
Exactly, yeah. It's flash memory, it's rewritable, and it's non-volatile. So you load your program in, and then you take your chip out of the breadboard, and it's got your program in it. So now you plug it into whatever circuit you want to use, and as soon as it gets power, it starts executing your instructions. And it's really fun to do. It's the one big thing that's missing being online. But it's pretty satisfying to actually go through the whole process. So yeah, so question about loop. So loop is really just a convenience, right? The way this code is working, and like I say, we'll talk about control instructions later, but the way this code is working, we're doing a MOVFF, a MOVF, an exclusive OR, an AND, a bunch of stuff like this. And then at some point down here, we want to go back and we want to repeat our code from this point on. So this is an instruction to the assembler, to the IDE, saying, hey, I want you to make a note of what the address is in program memory of this instruction. And then down here, when I say go to loop, I want you to go to whatever that address is that you remembered. So it could be called anything. Yeah, we could call it, loop 1 or Fred or Betty or whatever. It's just a symbol.
So it's really just going to the first statement of that.
Of that section of code, yeah.
Okay.
So down here
Or
is...
is it just going to the naming convention that you gave it?
It's going to the first instruction after wherever you put that name in your source code. So like here's a label INCL, so when I say call INCL, it's going to jump down and execute this instruction, and then the next one and the next one and so on. Indents only matter as far as are you in column 1 or not. If you want a label, it's got to start in column 1. If you want a number sign define, I believe that has to start in column 1. If you're doing an EQU statement, it has to start in column 1. Most other statements, origin, opcodes, things like that, the end statement, have to start after column 1. But the amount of indent is up to you. The indenting between the opcode and the operand is up to you. It has to be at least one space. The indenting between the end of your instruction and the comment is up to you. It can be 0 or more spaces. But it's nice to, you know, make things so that they like line up nicely and are easier to read. You can use tabs, definitely.
I have a question. So in the lab, do you want me to, on column 1, start with the define statements? Because I know on the top there's like a lot of notes. Yeah, like the file, description, date. Do you want me to just delete that and start with the...
I would put all of it in.
Okay.
Yeah.
Cool.
Don't worry about the list statement for now. Radix says default is hex, but I think every value is specified with 0x anyway, so that doesn't matter. And don't worry about this stuff. We'll talk about that later also. What does this code do? So when you run through it and you look at the values of the variables, that should tell you what's happening. So the procedure for the lab is to set up some watch points so you can look at the values of certain variables, and then to set up a stimulus so that you actually change the values applied to the pins of the chip. In particular, the pins corresponding to bit 0 of port A. And so if you do that, and then you hit the stimulate button, which will toggle the value of that pin between 0 and 1, and you step through it, you should see stuff happening. And that should help you figure out what exactly this program is doing.
So, when you said those memory addresses that are outside those 256 bits, you were referring to stuff like the pins, right?
Yes, exactly, yeah. And we will get into that starting on Tuesday as to what exactly this means and why we have 12 bits all of a sudden and so on. But it's a lot of kind of minutia, gory detail that that can like undo everything that we've learned so far. So I'm gonna defer that. All right, cool. So we've got directives. Two more things I want to go over. The first is this binary coding. We have enough to manage all of this this binary coding homework. So if you have an instruction like clear file register 23, we know how to write that in binary, right? 0, 0, 1, 0, 1, 0, 1, and then clear F. Let's do increment F. So 0, 0, 1, 0, 1, 0, and then if you're putting the result in the W register, this bit is a 0. If you're putting it back into the file register, this D bit is a 1. The access bit we haven't talked about yet. You can just leave it as an A for now. And then 8 bits that specify the file register. So 23, 0010, 0011, or whatever the bit pattern is for the file register. If you're given binary and you're asked what the instruction is that corresponds to it, now you got to do a hunt and seek puzzle. So if you're told that you have an instruction like 0 1 1 0 1 1 1 0 like this, and you want to know what this instruction corresponds to, well, you have to find a pattern somewhere in this data sheet that corresponds to these bits. So most of these instructions are differentiated by their first 4 or 5 or 6 or 7 bits. So you look for a 0 1 1 0, and there's some 0 1 1 zeros followed by a 1 1. So it's none of these. 0 1 1 0, and you just kind of go through. We need a 1 1. There's a 1 1 0. 0 1 1 0. might have given you a bogus instruction. Well, I picked one out anyway. Anyway, so if this is a 0. So 0 and 1, 0. And then there's a 0 and a 1 and a 1. So that matches the first 7 bits. And then this 8th bit, A, is a 0. And then there's a file register. And our file register looks like, if we convert this into hex. So how do you convert into hex? Break your number up into 4-bit pieces and write the hex digit corresponding to each. So this is hex. That's an 8. That's a 4. And so this looks like I lost it again. There's 0, 1, 1. Looks like a test FSZ. And the value of F is 0x84. And the A bit for us was a 1. So just put down the value of the A bit there. Don't worry about what the A bit means. So converting from assembly language to machine language, find the opcode, and then fill in the 1s and 0s. Going the other direction, you're given a pattern of 16 1s and 0s. You have to find the pattern in here. Find something that matches that pattern, and then the other bits, if it was this instruction right here, then the 7th bit would be D, and you know what that means. The 8th bit is A, which we're just going to leave as A, and then usually 8 bits for the file register. So play around with those. Like I said in the announcement, the homework is due on Thursday, so if you're not able to figure out the coding of those instructions, ask about it in lab or in class on Tuesday. So the other thing we want to cover is literals, and literals are critical to what we're doing. So here's the whole idea of a literal, right? So we understand that when we say INCF 0x23, this means increment the contents of a file register at location 23 hex. So we're not incrementing the number 23, right? We're reading the contents of a file register at location 23, and we're incrementing that contents. Okay, this gets a little confusing when we look at something like MOVF 0x23, W. This does not set W equal to 23. Okay, this sets W, the W register, equals the contents of file register 23. I should be consistent and use a 0 there. Okay, so this reads the contents of a file register. This increments the contents of a file register. So far, everything we've done, the operand is the address of a file register, and we're acting on the address. But there's an entirely separate set of instructions called literal instructions. And with literal instructions, the operand that we specify is literally the value that we're interested in. It's not the address anymore. It's actually a literal value. And there's a series of literal instructions. So for example, add a literal, and a literal, inclusive or a literal, move a literal. So let's look at some of these.
So like, if you wanted to add, I don't know, a magic number to a location, that would be a literal. Right?
That would be a literal, exactly. It's a good way to think of them as like magic numbers. So if I say move literal W 0x23, that says actually take the number hex 23, copy that into the W register. So it's not reading a file register at all. It has nothing to do with any of the file registers. It's saying put the number 23 into the W register. And fundamentally different from MOVF 23, 0. This reads a file register. This just takes the number 23, puts it into W. All right, so there's...
I'm having a hard time understanding the difference. The difference is just the file versus the number in the file?
Yeah, so let's...
Oh, it's reference. Oh, I get it. So it's like the bottom when you're literally just copying the address. You don't care what's in it, right?
Right.
Okay.
So let's look at our file registers. So let's say file register 23 contains the value 8. And let's say move file register 23, 0. So after I do this, my W register is going to be equal to 8. Alright, because this says read the contents of the file register. So go to location 23. What's in there? There's an 8. Okay, take the 8, put it into the W register. But if I say move literal 23 into the W register, my W register is equal to 23. So this would be considered an indirect reference in like C terms. This is actually saying I want to set W equal to the number 23. This is saying I want to set W equal to the number stored at location 23. If I can use the dreaded P word, this is a pointer. But I didn't say that.
Why is it dreaded? Pointers are cool, right?
Well, it depends. Depends how your brain is wired. And whether you've made it over the worst of the learning curve on pointers. Yeah, pointers are pretty cool. After you're done with Engineering 270, pointers will probably, if you've dealt with pointers and you had trouble with them, after 270 they will probably make a lot more sense.
Crossing fingers.
Yeah, yeah. Alright, so add literal to W, I'll just keep picking on 23. Right, if I say add literal W 23, this adds the number 23 hex, right, 35 decimal to W register. W register bumps up by 35, 23 hex. If I say add W file register hex 23, it's a totally different operation. It says take the current value in the W register, take the value at location 23, add those together, and like this, store the result back in 23. If I say comma 0, store the result in W. Right? This is using 23 as a location in memory. This is just using the actual literal value 23. Add 23 to a W register. So if I say...
I'm having a hard time understanding because as far as I was concerned, OX23 is a file, and then it has contents within it, meaning 8.
Correct.
So we're saying now that OX23 is the number and not the file.
Exactly, yeah, you've got it. Right, this says it's not a file register, it's just the number 23. If I say add LW1, I'm incrementing the W register. Now file register 1, might have the number 57 in it. I'm not going to add 57 to W. I'm adding 1 to the W register. So these literals, nothing to do with the file registers. It's just the number.
That's interesting, because that actually means that those specific files and the number within actually hold two different contents.
Basically, yeah. But it really the hardware for the CPU, when it sees the literal, it doesn't have to go out to the file registers at all. It knows what it has to add. It's actually part of the opcode. And if you look at the coding for these instructions, for like an add literal, these 8 bits down here are no longer a file register. It's just an 8-bit number. And if I say add literal 1 to W, this will be 0, 0, 0, 0, 1, 1, 1, 1, and this would be 0, 0, 0, 0, 0, 0, 0, 1. And that 16-bit pattern means add the literal number 1 to the W register. Alright, so we can add literals to W. We can do logical operations, ands and inclusive ors to W. Don't worry about LFSR until we get to about week 6. Don't worry about MOVLB. We can move a literal into W. We can multiply a literal by W. Don't worry about return. Subtract is a thing, and exclusive ors are a thing.
Where can I find this list again?
This is table 20-1 in the data sheet. So the data sheet's linked on Canvas. It's that 310-page document.
This is in the 18 pages that are super important, right?
But this is in the shorter version, yeah. The pages that I find most commonly used by me. But all 310 pages are important in their own way. Alright, yeah. So when it's not literal, yes, we're using a pointer, basically. Alright, so literals are useful for us. When you want to do things like add, 15 to a file register. So let's suppose we've defined, X to be some file register, and we want to add 15 to the value of X. Well, we could move a 15 into the W register. And then add the W register to file register X. And if I don't say comma 0, it'll put the result back into X. So these two statements will do X equals X plus 15. And this is why W register is a working register, right? It's the only thing into which we can move literals. I don't have an instruction to say move the literal value 15 into file register X. Right? W is the only register that we can move literals into. So anytime we want to use a literal value, we're going to have to use W. So W is really kind of a scratch pad register. It's a temporary thing that we use to hold literals, to hold running sums, things like that. But we usually don't store precious values in there that we intend to keep, for the duration of a program. It's just kind of a temporary thing. If we had a value in W that we wanted to save somewhere, what do? Well, we move it into a file register. So you could say move WF, save 7, and it would copy the value of the W register into this other save register.
Is the reason because of the way that the memory is handled within the files?
Yeah, so this is all related to decisions that the architects of the machine made when they were designing it. And
so
if
this is basically just the working memory.
This is the working memory. Yeah, it's a particularly convenient type of memory because we can save results in there. We can specify that we want a result saved in there by just using one bit in our instruction, just that destination bit, the D bit. Whereas any other file register, if we want to specify that the result should be saved in file register 75, it's going to cost us 8 bits to specify that. But the working register we can specify with just one bit. So it's a really easy one to say, do this operation and then throw the result in this temporary. but there's only one W register. And that's part of this being a reduced instruction set machine. So if you look at the data path here, there's the W register sitting down here. It's, 8 flip-flops probably, and that's the only one of its kind. Now, complex machines would have more of these internal registers. You might have 16, 32. x86 processors have several of these internal registers, but it depends on the architecture, and it's just design decisions that are made by the team that designs this. And again, Microchip makes this PIC processor. This is one out of hundreds or thousands of different kinds of processors made by PIC. And different processors have different architectures inside. So part of the challenge / fun of working in assembly language is understanding the constraints you have and being able to do what you need to do within those constraints. We have one working register. How do we, calculate a quadratic equation to find the 2 roots of an equation and then pick out the largest root? Well, you're going to have to break that down into some pretty small pieces. And C, we could do it with, some arithmetic expressions and a few if statements and, several temporary variables. In assembly language, that would be a lot trickier. But again, this is really the essence of programming. It's the essence of engineering. If you like Minecraft, this is Minecraft, right? You got these silly blocks. Here's a block of dirt. Here's a block of granite. Here's a block of wood, right? And you've got to build your whole universe out of these simple blocks. Well, you can't just build a house from dirt, right? But you can grow trees, and you can cut down the trees with your hands and make a pickaxe, and you can use those to get stone, and you can use stone blocks to build your house, And so, I mean, it's bootstrapping up from these simple blocks to more complex blocks. And that's just a feeling you're going to have again and again and again as we do more programming at assembly language. And inevitably, there's a point where our minds will shift to accepting what our fate is. And until you make that mental shift, assembly language is really frustrating for most people. It's like, why do I have to do all this stuff just to add 15 to something? Why is it so hard just to see if x is equal to 0, right? But once you understand kind of what you're dealing with, and you're comfortable with the fact that, I'm starting with trees and my hands and blocks of dirt, right? And I'm trying to build a castle, right? Once you understand that and you start working with that instead of fighting against it, then the stuff starts to get to be pretty fun. Because it's puzzle solving, right? And most people who are in this career like solving puzzles. So that's a bit of a sales pitch there. All right, so I'm going to ask you to do one more attendance check. Send me your Canvas name, dash, and the word here to let me know that you're here at the end of class. I will close out the room in a couple of minutes, and I will open the lab. If for some reason the lab link does not work, send me an email and let me know, and I'll double check it. But I didn't get anybody in lab on Tuesday, so I have no way of knowing if the link is actually working or if there might be a problem with that. So if anything ever goes wrong, send me an email. It usually reaches me quickly. All right, cool. Awesome. I'll see you in lab. And otherwise, have a good weekend, and I'll see you on Tuesday.
See you on Tuesday.
All right. Have a good one.
Have a great day.
Thanks, you too.
Thank you.